Welcome back to 8701. In this second chapter, we will discuss symmetries and the importance of symmetries in physics in general, but also especially in particle physics and nuclear physics. So we'll start with a short introductory video, and then we'll move on into more details as we go along. The importance of symmetries cannot be understated in physics. And there's two aspects which are important. The first one is that symmetries and conservation laws go hand in hand, as discussed by Noether's theorem. To express the theorem in an informal way, you can say that if a system has a continuous symmetry property, then there are corresponding properties whose values do not change with time, meaning that they are conserved. You can express this more sophisticated and say to every differentiable symmetry generated by local action, there's a correspondent conserved current. And we're going to look at those actions and currents as we go along. The second aspect, beyond the fact that there's conservation laws, is that you can understand physics experiments and nature if you know that the physics has an underlying symmetry without fully understanding the physics or the mathematical backgrounds in order to do calculation in detail. So knowing that there's an underlying symmetry can help really expressing or understanding the physics behavior of experiments. A few historic remarks on Emmy Noether. Emmy Noether was born in Germany in the 1880s in Erlangen, where she grew up and also studied mathematics at the University of Erlangen. After getting her degree, she worked for a full 7 years at the university in the math department and received $0. And not just because that wasn't the currency being used there, but at that time, women didn't really have a prominent role in academia, and so there was no job for her to take. But her talents and her qualification was seen in the mathematical world at the time, specifically in the center of the mathematical world, which was in Göttingen. So Hilbert basically discovered her and asked her to come to Göttingen in order to do habilitation. She did get an habilitation in Göttingen in 1919, and then stayed in Göttingen till the situation in Europe degraded in the 1930s. So she was born Jewish and couldn't stay in Göttingen beyond the year 1933, and then had to immigrate into the United States, where she worked at Brian Moyer College and also with Princeton. Her work, I mean, you see here her habilitation, which is in German invariante Variationsprobleme, invariant variational problems, was highly regarded, and she had a lot of influence and impact on various strands in mathematics and physics. Unfortunately, she passed away already, and she was about 50 years old. She, was diagnosed with some sort of cancer and passed away really, really quickly after some surgery. Her temperature rose, and a few days later, she passed away. To come back to symmetries and conservation laws, so every symmetry of nature yields a conservation law. That is what Noether's theorem tells you. And you can revert this to saying that every conservation law in physics reflects an underlying symmetry. And examples for this are the fact that the properties, the laws of physics are invariant under time translation, meaning that physics is the same yesterday, it's the same tomorrow, and it's going to be the same next week. And out of this, we can deduce energy conservation. Similarly, translation in space results in momentum conservation. Angular rotations or rotations result in angular momentum. And then a little bit harder to grasp, but we will see this in more detail. Internal symmetries can also lead to conservation laws, and gauge transformation leads to the conservation of charge. So there's internal symmetries as well. Before we dive into more detail, a few things, in many cases, symmetry operations can be expressed via matrices or groups. And there's a few rules or operations which are rather important and define the symmetry. So the first one is that any symmetry operation has to have identity, meaning there has to be an operation which doesn't do anything with an element of this group. There has to be closure, meaning that if you apply a first transformation and then a second, the resulting transformation is again as part of the set of transformations. There is an inverse, meaning that if you rotate in one direction, you can rotate back, and there's an associativity, meaning that if you have a rotation acting on two other rotations, you can regroup and follow what's shown in this equation here. It's not clear that you can revert the order of certain elements of your group or your symmetry operation. You can classify them, however, those where you can commute, those are called abelian groups, and those where you cannot, those are non-abelian groups. All right, so with this, we have introduced with the first video symmetries, and now we just dive into more detail in understanding continuous symmetries and also discrete symmetries and what we can learn from them.